that both the voltage and the current in that resistor are going to be in phase with each other. So for an example, if the voltage across the resistor will be at 0 degrees, the phasor of the current will also be at 0 degrees. When we come to an inductor, what we see is that the current IL lags the voltage. So if you are sitting at the voltage going to your current, you'd move in a clockwise direction, and that gives you a negative value of the angle. So for an example, if VL is at 0 degrees, IL will obviously, as you can see, is at minus 90 degrees. And what we also say as a matter of emphasis is that IL lags VL. So IL will be lagging VL. Now, if you have a capacitor, you can see that IC is leading VC. So if VC will be at 0 degrees, IC, the current through the capacitor, would be at positive 90 degrees. That means that the current IC is leading the voltage VC. Now, an important aspect also that we looked at is the power diagram. The power diagram, or what others refer to as the power triangle, which relates the various powers that we dealt with in AC networks. When we dealt with DC networks, if you remember very well, we only dealt with one kind of power, that is active power, P. But once you bring about an AC network and you bring about other elements such as capacitors and inductors, we introduce what we call a power triangle, because we would have an active power which is represented by P, and it's measured in watts. This is the active power. That's what does the useful work. And you'd have the reactive power which is represented by the capital letter Q. This is the power that is brought about in the circuit by the inductance and the capacitance. It is positive if you have got an inductance, so the inductance will bring about a positive. What does a positive inductance actually mean? It means that that element, which is an inductor, absorbs absorb reactive power. It's absorbing reactive power. And a negative Q, which is now brought about by a capacitor, means that a capacitor provides a reactive power. And this is obviously the apparent power capital S. And the angle between your active power and your apparent power gives us the angle, the phase shift angle, if you like, the power factor angle that it's brought about. Now, what is also important is in your representation of the apparent power, you write it as P plus JQ if, of course, in your circuit you have got a combination of resistors and inductors. If you have got a combination of resistors and capacitors, this would most appropriately be P minus JQ, and that minus JQ would tell us that you are working with a capacitive load, a predominantly capacitive load. And I've indicated to you that it doesn't mean that if, for an example, I've got P minus JQ, it doesn't mean that I don't have inductive component in my circuit. It simply means that the capacitive component is greater than the inductive component. That's what it means. And the resultant reactive power then is negative. So I'm generating more reactive power than I'm absorbing. That's what it tells me. Now, how would you calculate this apparent power when you have got two phasors? Is that you calculate apparent power by saying the voltage multiplied by the complex conjugate of the current, not the voltage multiplied by the current. Just a moment. You know complex conjugate, you have dealt with complex numbers. So if for an example, I being given as 2 plus 3j, I complex conjugate is 2 minus 3j. If I've got I being 14.5, angle minus 16.82 degrees, I complex conjugate is 14.5 angle 16.82 degrees. If I've got I as 20 angle 13.8 degrees, I complex conjugate, it's simply 20 angle minus 13.8 degrees. So if you are calculating and you find this to be your current, don't say S is equals to V times I. When you're calculating your apparent power, it will be wrong. It will be wrong. This will be wrong. If you are calculating your apparent power using a phasor voltage and a phasor current, you need to remember that you need to use the complex conjugate. And you would see that once you do that, it will give you, for an example, for your currents, rather for your powers, the correct notation. What I mean by correct notation, for an example, if you use the complex conjugate for a lagging current where the angle is negative, so a current is lagging, the angle is negative. If you say voltage multiplied by the complex conjugate, that angle becomes positive and you'll have P plus J times Q. For a lagging current, this would be the case. And that would be consistent with the fact that you'd have a positive Q, which is representative of an inductive load. Now, the apparent power S is the product of the voltage drop E across an element and the complex conjugate of the current flowing in the element. I've explained that. The apparent power S is the product. This is exactly the same thing as above. A positive value for P or Q indicates that the element is a load, that is, it absorbs active or reactive power. A negative value for P or Q indicates that the element is a source, that is, it delivers active or reactive power. Now, we will predominantly really work with a negative value of Q because we would really be calculating these parameters at our load. So we'll seldom want to calculate how much power does this source provide, how much active power does the source provide, and so on and so forth. We will seldom do that. Not that we can't, but it's not a common a problem that you can have. So just to indicate the difference between a source and a voltage. So just this just simply shows you how you can calculate your apparent power if you only have got a resistive load. So what does that mean? What does that mean if I only have got a resistive load? It means the following. It means that I don't have an inductive load. I don't have a capacitive load, right? Now, it means that so the value of Q is 0. That's what it means. I don't have the value of Q because Q is brought about either by the inductance or by the capacitance. So P is equals to S. Now, the apparent power will be equals to the active power if I only have a resistive load in my circuit. If I've got an inductive load, only an inductive load, I don't have a resistive load, I will not have any active power. I will have a positive value of Q, which would be given as VL squared divided by 2 pi FL, divided by XL, if you like, divided by XL. And of course, the same is true if I got only a capacitance. So if you like this, you can see this, for an example, the apparent power on your capacitance as VC squared divided by J omega C. Divided by J omega, divided by, or rather multiplied by 1 over XC. So you need to understand it as such. So omega C times VC squared, this is a representation of Q, right? Q, because P is 0, I don't have any resistive element in the circuit, and this is how I would calculate the Q. What is the Q? The Q is the reactive power produced now by the capacitance. Those are just examples and all of that. Now, we want to speak about a balanced three-phase. Now, what do we mean when we say communicated? So when we are speaking about a balanced three-phase network, what are we referring to? We are referring to the following, that you would have 3 voltages. Now, these 3 voltages are said to be balanced if the following is true. 1, if they are equal in magnitude, so they must be equal in magnitude and be out of phase from each other by 120 degrees. Now, if you have, and now this is one system, good people. So it's one system. How do you connect that one system? You do it like this. So you'd have, for an example, a voltage that's connected like that. So you can have it like that. Minus plus, minus plus. And this is a common point. So you can find that to be ER, EY, EB. So these sources, these 3 sources are connected together to a common point. So we can call that a neutral point. So the point of common connection. So we would say that these sources are connected in Y or star. This is a Y or a star connection, right? So you'd connect all these 3 voltages together. Or alternatively, you can connect them in delta, where you have got 1 star. So you can connect it like this, such that maybe plus minus like that, plus minus, plus minus. So you have got your sources connected this way. Let's call that ER, EY, and EB. So they are connected in this form. So this is what you call a delta or a pi connection. So pi as in pi like this, right? Yeah, but the most usage is the delta. So most of the time we will use delta. We'll use delta. That's the common usage of the way of this connection. We would use connected in delta, connected in delta. This one. Is equals to the magnitude of EY is equals to the magnitude of EB. In all of these instances, They are equal in magnitude. So if one is 120, all of them are 120. But they are out of phase from each other by 120 degrees. So that's what we want to explain. They are out of phase from each other by 120 degrees. So for an example, let's have a look at the red voltage. So you see, if the red voltage is at 0 degrees, the yellow will be lagging at 120 degrees, and the blue will be leading by 120 degrees. If you are at this point, at the red point, of course, here they are expressed in terms of pi, but here you can see they're expressed in terms of degrees. So this one will be at minus, if of course our reference in this instance is the red phasor. You can see that E yellow is at minus 120 degrees, E blue is at positive 120 degrees. Now, of course, another person can say, well, you can write this EY as positive 240 degrees, and it's exactly the same thing. It's exactly the same thing. Whether you say EY is at an angle of 240 degrees, or you are saying it's at the angle of minus 120 degrees, it's exactly the same thing. It means exactly the same thing, right? So that is what we are having here. Now let's have a look at a very quick example here, where ER is at. So ER, now it's our reference, is at 30 degrees. Now, what is EB and what is EY? Let's see how we can do that. Okay, canvas. So you'd have I can't write properly this way. Okay. Something like that. So this is ER, see them as equal. See them as equal in magnitude. So ER is there, it's our reference, that's EB, that's E. What we know is that ER, it's simply E angle positive 30 degrees. We know the magnitudes are the same because this is a balanced system. So, but we want to know where the others are. What we know is that they are also out of phase from each other by 120 degrees. So EY will be given as E angle 30 degrees minus 120 degrees. This is where EY would be. That is where EB is at. And EB would be E 30 degrees plus 120 degrees. Such that ER at E 30 degrees, EY would be at E. What is 30 minus 120 degrees? Minus 90. Minus, huh? What is it?
Yes, minus 90.
Minus 90. So actually, it means if you are to draw it properly, it has to be somewhere here. EY. Forget about that one. So, and then EB would be E at 150 degrees. So this will be your voltages. This will be your voltages. Now you will see, good people, why this is important, because when we give you information in a three-phase network, we only tell you an information of one and tell you that this is a balanced system. You need to come up with the others. So we don't say, for an example, you have got a three-phase system where ER is this, where EY is this, and EB is this. Then we don't give you that information. We give you one information, and then we also tell you that this is a balanced system, then you will have to come up with this particular information yourself. So it's important for you to see how it comes about. Right. So now back to the slides. So we can find where exactly this is and where that is. Right. That's fine. So I've indicated here that if this is where your ER is, you can write this in terms of 120 degrees or 240, but as a matter of principle, we stick to the conversion where we relate to them on the 120 degrees scale. So if this is at 0, we will say EY is at -120 and then EB will be at -120. So if you like, you can forget about the 240 conversions. They are equivalent, but we seldom use that. Now, there's a very important thing that we need to learn now is what we call a sequence. Now, this voltages are not at random, right? They are not at random. What do I mean they are not at random? I mean that there is a particular sequence in which they are following each other. They are a particular sequence in which they are following each other. So for example, if you look at this waveforms here, you can see that if we start this is the starting point and we look at it, you'd see the red phase peaking at some time there, followed by the yellow phase and followed by the blue phase. So what are we saying? We are saying that actually the yellow phase lags the red phase by 120 degrees. We can see that, we know that. So it would peak 120 degrees later. So if you take the difference between where this red waveform and the yellow waveform peak, that difference would give you 120 degrees. But noting that this yellow phase is delayed compared to the red phase. And of course, if you take it from the red phase to the blue phase, you will see that the total here is at 240. So it would only peak 240 degrees later than the red phase, or 120 degrees later, it would lag the yellow phase by only 120 degrees. So that's what you'd have. And of course, if you go, you know, a little bit before this 0 point here, you would see also that the blue phase would peak at some time before the red phase. But of course, if our reference is at 0, then we want to look at all our waveforms with reference to the red phase. But technically speaking, at some point the red phase is itself lagging the blue phase. And so you have got all of that taking place. But for consistency's sake, we would want to stick with the red phase as our reference. Now, I want you to look at this. Where you have got, if we have got the red phase at a particular angle phi, be it 0, be it whatever, a positive sequence means that the yellow phase will lag the red phase by 120 degrees, and the blue phase will lead the red phase by 120 degrees. The yellow phase will lag the red phase by 120 degrees. The blue phase will lead the red phase by 120 degrees. But on the negative sequence, we still have the same red phase at whatever angle, be it 0, be it 10, be it 30 degrees. We find that the yellow phase on the negative sequence is now leading ER by 120 degrees. And the blue phase is now lagging ER by 120 degrees. What does that mean if I was to write it down? Now, what does that mean? It means that for a positive sequence, if I've got a positive sequence, I've said that, let's say this is where my ER is. And this is where my EY is. And this is where my EB is. 120 degrees, 120 degrees. So if I've got ER as E angle 0, EY is E angle minus 120 degrees, EB is E 120 degrees. Now, once I have this sequence, I'll say this is a positive sequence. Now, this positive sequence is also represented as red, yellow, blue. Sometimes we use subscripts A, B, and C, and in that case, if we say A, B, C, then or sequence A, B, C. That would be a positive sequence, but you mostly would use the red, yellow, blue notation. We use the red, yellow, blue notation. On the other hand, for a negative sequence, you'd have ER and you'll have EB here. You'll have EY here. So that is at positive 120 degrees. This is at minus 120 degrees. And of course, the same is the same. This is the same ER. It's E angle 0 degrees. EB, it's E minus 120 degrees. EY, it's E 120 degrees. And this is now called a negative. This is now called a negative sequence. Which is represented as red, blue, yellow. Or if you like, and this is A, this will be C, that will be B, A, C, B. So you can have, for an example, A, B, C, and A, B, C, and then you say one is positive, the other one is negative, right? So you'll have it this way. Red, yellow, blue, or ABC, then we know that that sequence is positive, or red, blue, yellow, or ACB. Once we have this, we also know that that is a negative phase sequence. Now, how does the sequence come about? It's that we would say, if you were to rotate this phasor diagram counterclockwise, if the rotation, you were to rotate it counterclockwise like that, and we follow the chronology of the subscripts of this. So you'd see that if I start at this point 0, I will have the red followed by the yellow, followed by the blue. If I was to rotate this phasor diagram counterclockwise and look which subscript comes and is followed by what, and then which one comes last, you can see that the sequence, how they will follow each other, will be such that it's the red that will start, followed by the yellow, followed by the blue. And once that is the case, then we know that it means this is the sequence which these waveforms will follow each other. But on the other hand, if you do the same thing, you were to rotate this like this, you can see that the red will be followed by the blue, and lastly would be followed by the yellow. If, of course, we start rotating at this point where we take red as our reference, we move in a counterclockwise direction. So you would find the red followed by the blue, followed by the yellow. And the same is true for the subscripts of A, B, and C. Now, this is very important. Why this is important? Because if I say positive sequence, the angle of EY is different, completely different. When I say negative sequence, it's completely different. So if you miss giving me at the beginning the correct angles of these voltages, you might as well stop the problem there, because there is no way you're going to get it right. If I say positive sequence and you give me this, everything will be wrong, because once EY is wrong, EB would be wrong also. So you'll have swapped them around completely. So that is very important for you to note. So yeah, that's just the indication here of the sequences, how they follow from each other. So you can see the positive sequence. This is the positive sequence, the red, the yellow, the blue. So there's your red, there's your yellow, there's your blue. The negative sequence, there's your red, there's your blue, there's your yellow. And you can see the red now followed by the blue, and then later on followed by the yellow. Right. Any questions before we come to the load? I just wanted you to understand the waveforms in three-phase. We will explain in the next class issues of, for an example, line voltage and phase voltage, as well as the load, balanced load, what we mean by a balanced load, and maybe the various connections that you can have in the system. Now, what I mean by the various connection, I mean you're now connecting the sources, the three-phase sources, to your three-phase loads. Any questions? If there are no questions, good people, I think let's meet each other. Let's continue our classes tomorrow. Thank you.
Sir.
Yes, and then proceed.
Sir, I had a problem with logging into Proteus, so I only managed to download the Pirate application yesterday. So I was asking if is it possible we can extend the submission date?
No, sir, it's not possible. Okay. So why must I extend? Because you downloaded this thing yesterday?
No, I had a problem logging into that one, so I couldn't use that one. I'm using a different one.
Many students had problems with it. They struggled and they eventually got it. So because you cracked it yesterday, then we must find a new date, because Mr. Sindane couldn't get this right. We must now find a new date, all of us. I don't think it works that way. Then tomorrow or whenever someone will say, but say I got it also yesterday myself. Can you please extend? Like you extended. I don't think it works that way.
Okay.
Yeah, we had ample time to do this. Okay, thank you.
No, sir.
Yes, Mr. Gekan.
Yes, I wanna ask about the single phase, the power diagrams. Sir. Does it vary, say, from the inductor one, the capacitor one, and the resistance, or is it the same, the power diagram?
So the power diagram Let me write it here. So the power diagram is like this, né? So because in our load, you'll have a positive resistor, right? So you'll always have a positive value of P. P is greater
I
than...
can't see your screen.
Huh? You can't see my screen. Oh, sorry.
Yes.
Sorry about that. Okay, so this is what you would have, right? P is greater than 0. That is for R greater than 0. So that I have got some resistance in my set. I will always have a value of P, that is your active power, in watts. Now, if I have got an XL, I would also have some value of Q, which is greater than 0. The Q is positive. And of course, I would have S there. This is the angle phi, which tells us the power factor. So if I've got XL, so my Z would have to be R plus JXL. This is going to be my power diagram. If I've got XC, I would have Q being less than 0. Q that's less than 0, meaning that the Q which is negative. And I would have that being my S there, capital letter S. And of course, this being angle theta. Now, you can see that it doesn't matter whether I have, and of course, yes, I've indicated here. So your Z would be R minus JXC. So it doesn't matter whether you have got an inductive load or a capacitive load. P is always positive because I can never have a negative resistance. Resistance is always a positive quantity if I have that. Now, and in both instances, you must see that I have got the R component. I have got the R component. So this P is the R component. It's brought about by the R component. Now, this Q, which is positive, is brought about by the XL component. That is your inductance. So in the circuit, I'll have an inductance because this is the inductive reactance. Now, if I've got a C, a capacitance, this is the capacitive reactance, I'll have a minus JXC. This just simply tells us that this is producing reactive power, this is absorbing reactive power. That's how you draw your power diagram. So, for an example, when you did power factor correction, you started with this. And then we ask you to find the capacitance required maybe to reduce the power factor. That is, to reduce this to something like this. Right, so we want this Q to come to this Q nu now. So this angle will be reduced. Then once you do this, your power factor will be high. You have a higher power factor because this positive Q would have been minimized by this negative Q. But that's power factor correction. And I've explained that, I think, already. So yeah, this is how you draw them, sir. This is how you draw them. Does it make sense? Are you answered?
Yes, yeah, so that's yes, 100%.
Thank you very much. Thank you. Okay, that's it from me. I see you again. We speak again tomorrow. Thank you.